This is NeuroCave Plus, an application for exploring synaptic plasticity. NeuroCave Plus enables free-form exploration of neuronal or connectome data sets through node link diagrams with various edge, node, edge display, and display settings, pre-computed topologies, and data-derived color codings. It allows for exploration of synaptic plasticity with side-by-side views that are linked, so anything that's clicked on one side is selected on the other, and vice versa. Used to compare sequential or distant simulation steps in coordinate systems, and color codes can be set to track the evolution of engrams to achieve new steady states. NeuroCave Plus is built on top of NeuroCave. The original NeuroCave was designed to facilitate the comparison of structural connectomes or functional connectomes of actual human brains. Here's an example where on the left side, the topology is set to the anatomical coordinates, whereas on the right, it's set to the t-SNE embedding, and there are several different topologies, including isomap, or MDS, that's multidimensional scaling. These are different ways of performing dimensionality reduction and visualizing the brain in its native intrinsic topology. It basically moves regions of interest or nodes that are highly connected closer together to allow for a better visualization of the intrinsic topology of the connectome. And NeuroCave has been used to find differences in like the default mode network between males and females and people with different neurological conditions or psychiatric conditions. They have color mapping features that can show the color coding of different features of the graph theoretical properties, such as the Rich Club or module connectivity, or whatever the colors map to, can be clicked in the legend to make them translucent or transparent, to customize the display and highlight regions of interest. There's also a VR mode. The added features in NeuroCave Plus boil down to scalability and usability features. Some of the scalability features include, the original NeuroCave used a dense matrix for the edge connectivity matrix, so we redesigned that as a sparse matrix, and also instead of a CSV file, we have the option for pre-processing that into a JavaScript JSON object, which allows for faster loading and allows for switching of time steps and subject matter more quickly. The original NeuroCave allowed for the scaling of nodes, and what NeuroCave Plus does is it allows for the independent scaling of the left and right nodes, as well as boxes and cubes. NeuroCave Plus also implements these edge particle animations that show the directionality of edge connections. These particle animations that glide from the source to the destination along the edge really shows the flow of traffic in a simulation. The simulation step 90,000 that starts with no edges and allows for edges to organically evolve over time. So after 90,000 steps, the UMAP transformation shows the formation of a line attractor, which in the literature has been known to signify the first memory engram emergence. Later we'll see that the structure forms a little sooner at 50,000 steps in some of the lesion and stimulus simulations. So on the right, you see original anatomical brain coordinates, but the color code is UMAP, which is shown on the left. So the patchwork applied to the UMAP transform is shown overlaid onto the anatomical representation, so that you have a reference frame of how the different regions of the UMAP transform map onto the original simulation coordinates brain. This can be turned the other way by switching the color coding to anatomy. Now the patchwork pattern is seen on the anatomical brain, and the mapping from anatomical to the UMAP linear attractor is a little bit more visible. This allows you to select nodes in the patchwork region of your choice, and it shows where those are in the other view. This view shows on the left an isomap transform where the octahedral topology of the calcium data set at about 80,000 steps is visible. And this view shows on the left the isomap transform where the roughly octahedral intrinsic topology of the 50,000 millisecond timestamp of the calcium target variable data set. This isomap view organizes the nodes into clusters of highly connected nodes, and they form this octahedral shape. The right side shows the distribution of the nodes and their color codes in the UMAP transform, which shows the linear attractor more clearly. Here we have two time steps of the same simulation. On the right, there's the 60,000 millisecond time step, and on the left, the 70,000, and they're both in UMAP topology representation with the calcium heat map coloring. So these turn into like a 3D heat map where hotspots can be seen. Over here, the 60,000, there seems to be a pretty good deal of blue nodes, which are pretty high on this number scale, blue and violet. We control the sizes of the cubes independently, so we can make them big so that we know where they are. Then the shrinking of the blue patch between the 60 and 70,000 millisecond level timestamps might indicate a cooling off in terms of the calcium levels. Here we have an ensemble exploration where the left view shows the lesion data set at 50,000 milliseconds, and the right shows the stimulus at the same time stamp, both showing the UMAP transformation and both showing the anatomy color coding so that the original patches are superimposed upon these linear attractors. So the line attractors first form at the 50,000 millisecond timestamp in these lesion and stimulus data sets, which is a little bit faster than they did for the original burn-in data set. We can use the independent scaling to scale just the cubes to find out where in these linear attractors the stimulus neurons or the lesion neurons are. Make them really big so they stand out. Those are the ones that stayed together between the two topologies, whereas in the stimulus data set, they seem to be a bit more spread out. They seem to be integrated in the center, whereas the lesion ones are along the outside. Well, these are some interesting insights that can be gained from visualizing transforms of the ensembles in this way. The stimulus neurons seem to occupy a lot of this unwrapped coil over here, whereas in the lesion data set, the unwrapped portion of the UMAP transform doesn't have any of the lesion nodes in it. That's another insight that can be interpreted. This distant time step comparison for the same simulation, where a calcium target variation data set at 40,000 milliseconds, which is before any engrams form, is compared side by side to the same data set at 150,000 milliseconds, where it has potentially already achieved steady state. The node regions map to one another here. Click on nodes in one color representation. These are both in anatomical color coding, so the nodes that were in the same patch on the original brain-shaped brain are colored when they're same colors here, so you can see how they have been stretched and morphed in these topologies. You can click on them, like the threshold mode, to see the edges. This is where it's useful to toggle all of the node visibility so that all the nodes are made translucent. You can see the edges. So you can see that even though the same number of nodes are selected on both sides, there are only a few edges, the 50,000 millisecond time step, whereas there are many more edges in the 150,000 millisecond time